Here's part 2 of today's mini lecture on estimators, or estimates and estimators. Here's part 2 of today's mini lecture on estimates and estimators. What I want to talk about now is the idea of measuring the goodness, and yes, that's a technical term, of an estimator. So we're going to talk about something called the mean squared error of an estimator. And we want that error to be as small as possible. So if you have two different estimators of a parameter, the better estimator is the one whose mean squared error is less. So let's get to it. Let x be a random variable that has some parameter that we're going to call theta, following the book, that we want to estimate. Suppose we define an estimator we'll call it theta hat. Based on a sampling of x. And we want to measure how good this estimator theta hat is. So a comment on this notation. The book generally uses a hat to denote an estimator, and it puts a hat on the symbol for the parameter that's being estimated. There's some variations in that we'll see. For example, we have a mean as a parameter that we work with for random variable, but the sample mean is an estimator we have that allows us to approximate a population mean. Notice the notation for the sample mean is different from the hat notation. Our book would say that's the same thing as saying mu hat. Okay. I will probably tend to use the x bar notation for the sample mean, but just so you understand, there's a convention that the book is using with the hats, and there are some special cases where we don't use the hat. It's not like statistics tries to make our life easier. Better, but sometimes not easier. Okay, so we've got a parameter, we've got an estimator for that parameter. Because our estimator is based on x, samples from x, and because x is a random variable, our estimator is also a random variable. So it has things like a mean, a variance, a standard deviation. So we can use that when we talk about an estimator. But also, because our estimator is a random variable, it has bias and error. And I mean bias in the sense that we've talked about it before, right? Bias, it's the mean minus the actual parameter that we're trying to estimate, and the error is the standard deviation of the random variable. So what we want to do is we want, when we're looking for ways to estimate a parameter for a population, we want an estimator that's good, that has a small bias and small error. Or, you know, maybe we can't separate them, but together we want those differences to be small. The way our estimator deviates from the parameter, we want that to be small. So what we do is we take these two sources of error, and since they both contribute to the error, we're going to add them together. But these both could be positive or negative, and we wouldn't want them to accidentally cancel one another out and artificially reduce a representation of their error. So we're going to square it, square each term. So now each of those sum ends is always positive, and this is what we're going to call our mean square error of our estimator. So notice this estimator is put into the subscript of the mean square error notation. And this is what I'm going to talk about today. So let me highlight this. That was important. There's another formula for the mean square error that is illustrative. Turns out the mean square error can also be calculated using this formula. The mean of the difference between our estimator and the parameter, and square it. So this is a random variable. We shift it to the left or right by the value of the parameter. We square that random variable and we ask what's the mean. So the formula for this is exactly the same as the formula for this. But it's the second one that gives this formula its name, mean squared error. This difference here is the error, right? It's the difference between our estimate and the parameter. That's the error. You square it, so that's the squared error. Let's write that in here for emphasis. This whole thing is the squared error. And then you're calculating the mean of the squared error. MSE, mean squared error. This formula is just easier to work with. So let's play with this a little bit and see how this works with given estimators. So what estimators do we know about? Well, our favorite estimator is the sample mean. So let's talk about the sample mean. Let's let x be a random variable. With mean mu. Then the sample mean is an estimate for the mean that works as follows. So let x1, x2 through xn be separate independent trials of x. Then the sample mean, x bar, well, let's do this slightly differently. X bar, because it too is a random variable, it's 1 over n times the sum of these separate independent trials. Okay, it's our estimator of the mean. So if you like, we could write mu hat. I'm not going to. I'll just put it there for you to enjoy. So what's the mean square error of this estimator? Let's calculate it. So the mean square error of the sample mean, so by definition of mean squared error, that's the mean of the sample mean minus the actual parameter value, and we'll square that, plus the variance of the sample mean. In part 1 of this mini lecture, we showed that the sample mean is an unbiased estimator. No matter what your random variable is, the sample mean is always unbiased. That means that this is always 0. So to calculate the mean square error of the sample mean, we just need to calculate the variance of the sample mean. So we'll go back to our lecture from last time where we talked about linear combinations of random variables. Here the variance of our sample mean, well, that's the variance of 1 over the sum of the xi, and here the I are going from 1 to n. Right? This is the formula right here. So, got a scalar 1 over n. I can pull that out as a multiplier on my variance. It comes out as a 1 over n squared. And then we also saw that the variance of a sum is the sum of the variance. So I can write this as the variance of x1 plus the variance of x2 all the way to the variance of xn. All these random variables are just x, really. And so this is n times the variance of x. That n there cancels with that n there, so my mean squared error is 1 over the is the variance over n. Mean square error of the sample mean is 1 over n times the variance of x. So that's good. It also shows us that as our sample size increases, our mean squared error decreases. Because the bigger n gets, it doesn't change the variance, but the bigger my sample gets, the smaller this number gets, the smaller my mean squared error gets. So there's your first mean squared error calculation. And it's for our favorite estimator, the sample mean. So let's do another example. This is an example that's in the book. I'm just going to work it out for you in more detail. I think it's like example 468 or something. Let's consider the sample variance. Of a random variable x. And let's say it's got mean mu and variance sigma squared. We won't say anything more about the random variable. We've seen, well, here's the definition that we took for the variance, the sample variance. And I'm going to put a little small xi here just to emphasize that we take a sample of size n. So this is the example that, or this is the definition that we took earlier on in the course, and I noted we're dividing by n minus 1 and not n. Right? A person could say, well, let's define a different estimator for our variance, where we actually divide by n instead of n minus 1. So here's the estimator we defined before in the class, and here's an alternative estimator for the variance. And the only difference is what we're dividing by here. This is a true mean of the variances. This here is a slightly different calculation for a variance. let's look at the mean squared error of both of these estimators and see how the mean squared errors compare. Okay, so first I'm going to calculate the mean squared error for the sample mean or sample variance as we defined it earlier in the course. So, using the definition of mean squared error, the mean squared error of our sample variance is going to be the expected value, or the mean of this estimator, minus the variance. Square that, and we're going to add the variance of our estimator. So this is what we've got to calculate. We've got to calculate two things. This difference, so we have to calculate this mean of our estimator, and we have to calculate this variance of our estimator. So good news, we're not going to grunge through that. I'm going to give you a claim. So here's some facts that we'll use. Fact number 1, the mean of our estimator is our variance, our random variable's variance. That can be proved, that can be shown. The second fact is that the variance of our estimator is 2 over n minus 1 times sigma to the 4th. So the variance of our estimator is this constant times our variance squared, the variance of x squared. Yeah, maybe it'd be good for me to do that. We can put the x down there. And then the last fact I'm going to share is that if we look at the other estimator, right, what differs by that? The other estimator, well, I guess it's obvious to see. We'll use it later. Is it differs by our sample variance by a constant multiple, and the constant multiple here is n minus 1 over n. So let's use these facts to do the calculations that are going to follow. So back to this. Here, because the mean of our sample variance equals the variance of our random variable, this is 0. So it tells us that s squared is an unbiased, or the sample variance is an unbiased estimator. So for our purposes in this calculation, this means that the mean squared error of the sample variance equals the variance of the sample variance. And we're given that that sample variance has variance. I'm looking for it. Oh, no. It's this right here, right? 2 over n minus 1 times r, the variance of x to the 4th power. Okay, good. So we have calculated the mean squared error of the sample variance. Mean squared error of the sample variance is this. So now let's calculate the same thing for this other point estimator. So second, calculate the mean square error for this other estimator of the variance. By definition, the mean squared error for this estimator is the mean of this estimator minus the actual thing we're trying to estimate, and then we square that. So the mean of our estimator for variance minus the variance squared. And then we add to that the actual variance of our estimator. Okay, So here's where we're going to use this nice fact, because this fact here, that our other estimator is just a constant multiple of our sample variance. So going to this formula, let's write this. The mean of our estimator is the mean of n minus 1 over n of the sample variance. And by properties of the mean that we've talked about before, this is n minus 1 over n times the mean of the sample variance. And we're given here in the claim that the mean of the sample variance is our variance squared. Right? So this is good. But now let's look at this difference. So the bias is, okay, we just calculated this, and we're going to subtract the variance. And what do we get? Well, n minus 1 over n minus 1 times our variance. And I don't have much room, but you can check. It's minus the variance squared over n. So, calculation done. Step back a second and notice this is not 0. So this tells us that our alternative estimator for the variance has bias. It's a biased estimator. And if you go back and look at our conversations where we introduced the sample variance, I mentioned that we chose this here because of bias. And this is the day where we see why that n minus 1 is important. If you don't use it, you get bias. All right, moving on. Let's look at this number here. The variance of our estimator what do we do for this? Our estimator is a multiple of our sample variance. So by properties of the variance that we talked about last time, we have this. And our claim tells us what this is. So I'm looking at my notes. I think our claim says the variance of our sample variance is 2 over n minus 1 times the variance to the 4th power. All right, cool. So that n minus 1 cancels with one of the n minus 1s up here, leaving that n squared unaffected. So I get 2 times n minus 1 over n times variance to the 4th power. Putting this with the above, we get the mean squared error of our estimator is the sum of the squares of the sources of error. So I have the bias squared plus my variance. And again, I've got that x there. So let's simplify this a little bit. I get 1 over n squared times variance to the 4th plus 2n minus 1 over n times variance to the 4th. Let's pull out those. Oh, I've got an error here. Let's pull out the variances and we'll see this simplifies to this. And work out on the top, it's 1 plus 2n minus 2, so it's 2n minus 1. So we get 2n minus 1 over n squared over our variance to the 4th power. That's the mean squared error for this other estimator. Let's go back here. That was our mean squared error for, yeah, it was right here. This is our mean squared error. The sample mean. Let's see if we can get that to paste here. Oh, don't tell me. Oh. Mean squared error is 2 over n minus 1 times the variance to the 4th. Those are our two errors. And we want a mean squared error, or rather, step back. The idea here is an estimator is good if its mean squared error is small. That leads us to being able to say things or ask questions like, which of these two estimators is better? Well, with a logic based on mean squared error, the better estimator is the one whose mean squared error is smaller. So there's a claim to be made here that the mean squared error of our alternative estimator is actually less than the mean squared error of the sample variance. So I'm going to show you that. It's just a straightforward algebra calculation. But on the basis of mean squared error alone, it would appear that this other calculation or estimation of variance is better than the sample variance, the one that we're going to use. Well, think about that. So how does this work? Well, let's look at the mean squared error of the sample variance minus the mean squared error of our alternative estimator. That's 2 over n minus 1 over the variance squared minus 2n minus 1 over n squared of the variance squared. Putting those things together, pulling out the variance squared, we get that. Now simplifying what's in the parentheses there, so we get 2n squared minus n minus 1 times 2n minus 1. That'll all be over n squared times n minus 1, and all times my variance squared. So let's multiply out this thing on the top on the right. It's a 2n squared minus n minus 2n plus 1 all over n squared n minus 1, all times the variance squared. Notice we've got a positive 2n squared out here, and there'll be a negative 2n squared here, so those are going to cancel. And so putting everything together, I get a 3n minus 1 over n squared times n minus 1 times the variance squared. Anything to the 4th power is always positive. Our n, our sample size, it's going to be a pretty big number. But as long as it's bigger than 1, n minus 1 is positive. N squared is always going to be positive. So my denominator here is always going to be positive. And my numerator upstairs is always going to be positive. So this thing is always positive. So this shows me that this whole thing, a positive times a positive, is positive. If that's true, if this difference is positive, it means that the mean squared error of the sample variance is is bigger than the mean squared error of this alternative estimator. So on the basis of mean squared error alone, a person could conclude that this other estimator is better. That is to say, this estimator is a better estimator of variance of a random variable, not this one. So I will ask you to think about, why is it that we prefer this estimator? All right, I think that's it for today. Oh, not here. Let's do one example. So let's do an example of calculating the mean squared error for an estimator. We've done mean squared error for a sample mean. We've done it for the variance now, and hence for the standard deviation. Let's do it for sample proportion. This is another estimator we've talked about. So let's let x be a random variable that's distributed like a binomial with parameters n and p. And let's let p hat be the estimator for p. That's defined in the standard way, where you take a result from x and you divide it by n. So let's calculate the mean squared error for this estimator. So by definition, the mean squared error for the estimator is the mean of the estimator minus its expected mean, and minus the parameter we're trying to estimate. That's what goes here, right? We're trying to figure out what p is. You square that difference and then add to it the variance over estimator. So we've already calculated in class that this particular estimator is unbiased, right? And this term in here, the mean of the estimator minus the parameter value, that's called the bias of the estimator. And we know this estimator is unbiased, so this is 0. So this term is 0. That means that we just have to calculate the variance for our estimator. Well, here's where we lean on our previous work on parameters for linear combinations of random variables. The variance of 1 over n times x, that's 1 over n squared times the variance of x. Now our x is a binomial random variable, so we've got a formula for the variance of that. Let's continue our calculation up here. We've got 1 over n squared, and the variance of a binomial random variable is n times p times 1 minus p. So that n will cancel with one of those n's, and we end up with p times 1 minus p over n. So there's the mean squared error for this particular estimator of a population proportion. Okay, I'll stop there. Thanks. See you on the other side.